Okay, let's unpack this. Today we are conducting a complete deep dive into a topic that bridges, the most fundamental aspects of physics and chemistry with high-stakes operational design.
Armament technology.
Armament technology. We're talking artillery. Our mission here is pure concept clarity, structured revision, and ensuring you, the learner, understand not just the definitions of these complex systems, but the core engineering trade-offs that dictate why a gun is built the way it is.
Precisely. We are moving beyond the simple idea of just big guns. We're really focusing on the synergized and orchestrated application of all firepower assets.
So the systems approach.
It's a total systems approach. We're integrating structure, mechanics, ballistics, and explosives. We'll start at the chemistry of the propellant, move through the brutal physics happening inside the barrel, and end with the modern pursuit of first-rate capability and predicted fire.
And this material demands a professional, authoritative grasp of the language.
Yes, of precise terminology, and that's exactly what we're delivering today.
Let's start at the very beginning then, defining the role. When the armed forces talk about artillery, what are they really discussing?
They're discussing the integrated application of firepower aimed at destruction, neutralization, or suppression of the enemy. But physically, when we talk about the gun, it's really a two-part system.
Right. It's not just one monolithic piece of metal.
No, not at all. We break the equipment down into two primary components that have to work in perfect mechanical synergy. First up, we have the ordnance.
That's the firing half.
That's the firing half. The barrel, the chamber, the breech mechanism. Its singular job is to manage that internal explosion, load the charge, and then discharge the projectile safely and consistently.
And the second part?
The second part is the carriage or mounting. This is the critical support half. It provides the system's mobility, it ensures handiness in tactical situations, and maybe most crucially, it absorbs and manages the colossal forces generated during firing.
So it's all about providing stability.
Exactly. Stability is key.
Now, you mentioned a carriage or a mounting. There's a vital, if subtle, distinction there that really dictates how those firing stresses are managed.
It is a subtle but very important distinction, and it relates directly to those stability dynamics. We define a carriage as the structure that fires with its wheels remaining in contact with the ground.
Okay, so think of the classic towed 105mm light field gun.
That's the perfect example. The ground resistance, the friction, along with the trail, all work together to manage the recoil. Conversely, a mounting refers to self-propelled or fixed equipment that fires without the wheels in ground contact.
Like the 155mm K9 Vajra.
Precisely. In that case, the firing stress is managed almost entirely by its complex hydropneumatic recoil system and, of course, the sheer mass of the vehicle itself. Understanding that difference is really key to understanding the trade-off between mobility and sustained rate of fire capabilities.
We've established that artillery is primarily designed for indirect, fire-hitting targets that the gun crew can't visually see, relying on forward observers or radar.
That is its core function, yes.
But what about when things get up close and personal?
Well, while its core function is indirect support, every single artillery piece retains the capability for direct fire. This is reserved primarily for self-defense or for, critical battlefield situations where a hard, pinpoint target needs destruction.
For example, an enemy bunker or an observation post.
Or defeating enemy armor that has broken through the lines. This dual capability ensures the weapon is not instantly redundant in a rapidly changing tactical environment.
Okay, that makes sense. Let's talk about how the trajectory, the actual path of the shell, defines the weapon's role. We have a whole spectrum of capabilities here.
The tactical application is entirely driven by that trajectory profile. We can begin with guns.
Pure guns.
Pure guns. These prioritize range and velocity. They're characterized by a low, flat trajectory and a very high muzzle velocity. They excel at deep engagement and, as we just noted, can perform both direct and indirect fire roles very effectively.
And as we move up that arc, we find the workhorses of field artillery.
The howitzers. A howitzer is designed specifically for a high curved trajectory. This high angle of fire is engineered to provide what we call crest clearance.
The ability to fire over a hill.
Exactly. The ability to clear high ground, like hills or mountain ridges, to strike targets on the far side. They achieve this with lower muzzle velocities, and they typically fire heavier shells than pure guns.
And crucially, they use variable charges, right?
That's the key to their flexibility. They use variable charges. The amount of propellant can be adjusted to control the arc and the ultimate range, offering immense tactical flexibility.
So if you want the best of both worlds, the range of a gun and the trajectory flexibility of a howitzer.
Then you design a gun howitzer. These pieces combine the long barrels needed for high muzzle velocity and range with the reinforced structure required for high-angle fire. Most modern artillery in the medium and heavy caliber ranges, generally 155 millimeters and above, fall into this combined category.
It's about getting a single system to cover all tactical scenarios.
That's the goal.
So if the howitzer is good at clearing hills, how do we hit a target that's tucked away on the backside of that hill, totally out of sight in what we call dead ground?
That is the exclusive domain of the mortar. A mortar is fundamentally different. It's a very high trajectory weapon, typically smooth bore and muzzle loaded.
Almost a vertical flight path.
It's almost vertical, and that makes it ideally suited for dropping bombs onto targets in dead ground or on reverse slopes where no other ground weapon can really reach. They are the essential close support weapons for infantry.
Beyond these barrel systems, we have weapons focused purely on area suppression.
And that's where rocket launchers fit in. They're characterized by their capability for area saturation and their very high explosive, or HE, content.
That they're less accurate.
They are inherently less accurate than spin-stabilized gun ammunition, yes. Their tactical utility lies in neutralizing large, soft area targets like concentrations of enemy troops in the open, unarmored vehicles, or maybe preemptive barrages on assembly areas.
So you're trading precision for volume and instantaneous area effect.
You are. It's a different tool for a different job.
And finally, at the top of the pyramid, the most strategic layer of firepower.
The surface-to-surface missiles, or SSMs, these are reserved for long-range strategic engagement. We're talking ranges from 150 kilometers all the way up to 5,000 kilometers, offering unparalleled striking power against key infrastructure and strategic assets.
We also classify artillery by the size of the barrel bore, the caliber. And this isn't just a number, it dictates the entire logistical and operational profile of the weapon.
Oh, it absolutely dictates everything. Mass, mobility, destructive potential. We categorize them broadly. You have light or field artillery up to 120 millimeter.
Like the 105 millimeter light field gun.
A perfect example. Their selling points are a high rate of fire and, critically, air portability. This is essential for rapid deployment in mountainous or difficult terrain.
Then you have the middle ground.
That would be medium artillery, ranging from 121 millimeter to 160 millimeters. This is really the sweet spot where you start seeing a considerable lethal blast effect and longer range, but they are heavier.
Which reduces their tactical mobility.
It does. They often require dedicated prime movers or self-propelled chassis.
And then we get to the high end of destructive power.
Heavy artillery, from 161 millimeters to 210 millimeters, and super heavy, which is 211 millimeter and over. These are massive systems, optimized for large caliber shells and extreme blast effects.
Reserved for major destructive tasks.
Yes, like destroying heavily fortified positions or for counter-battery fire. The trade-off is unavoidable. They have a slow rate of fire and significantly reduced mobility. The pattern is clear caliber, weight, and rate of fire are all intrinsically linked design characteristics.
Okay, so we understand the categories, the what. Let's
Yeah.
pivot to the why, the fundamental military requirements that drive all of this design. What must a piece of ordnance deliver?
There are 7 core requirements that govern the design. Lethality is, of course, paramount. The system must achieve the desired destructive result at the target. But immediately after that are 2 concepts that must be absolutely clear for you, the learner: accuracy and consistency.
And they are often confused, but they are not the same thing at all.
Not at all. It's a crucial distinction. Let's unpack it.
Let's do that.
Accuracy is about targeting. It implies the ability to deliver a group of rounds so that the average center of that group, what we call the mean point of impact, is situated exactly on or closest to the target.
It's about being correctly aligned, pointing in the right direction.
Precisely. Consistency, on the other hand, is about quality control. It is the ability to deliver a tight group of rounds, a small, clustered shot group, regardless of whether that group actually hits the bullseye.
So to use an analogy, consistency is about mechanical quality control, getting the same result every time, while accuracy is about having the right data and targeting. You could have a gun that is highly consistent, firing a perfect cluster of 5 shells.
A very tight group.
But if that cluster lands 500 meters away from the target, it is still wildly inaccurate.
Exactly. And that's the key. The perfect weapon is both accurate and consistent. If the gun is highly consistent, the necessary correction, the aiming error, is small and very easy to apply once you figure it out.
But if it's inconsistent,
If the gun is inconsistent, the shot group is wide and dispersed, making any kind of accurate correction almost impossible. You're just chasing random impacts.
What other requirements dictate the operational design?
Well, operational readiness is essential. This demands a quick response time, meaning the detachment must be able to bring the gun into action swiftly and fire that first round. This has to be matched by a high and sustained rate of fire.
And flexibility.
Flexibility and mobility are vital. This includes wide range coverage, often achieved through those variable charges we mentioned, tactical mobility, so being towed, self-propelled, or using an auxiliary power unit, and especially for rapid deployment forces, air portability.
Which brings us right back to that fundamental design compromise we touched on earlier. The armed forces can't just maximize all 7 requirements at the same time.
No, the compromise is inherent in the physics. If you want to maximize lethality and a sustained rate of fire, you inevitably require a heavier, more robust ordnance system to handle the forces and dissipate the heat.
And that requirement is in direct conflict with the need for a quick response time and air portability.
Direct conflict. Every artillery piece, from the lightest field gun to the heaviest howitzer, represents a calculated, tactical compromise. It's a balance of destructive power against the tactical speed required to operate effectively on a modern battlefield.
Let's move to the 6 operating principles, the how. These are the physical laws that allow the entire system to function. We start with the direction of the barrel.
The foundational principle is initial direction. This direction is determined the moment the projectile leaves the muzzle, based on the barrel's azimuth and the projectile's predetermined velocity.
Newton's first law.
It's pure Newton's first law. It would travel in a straight line forever if it weren't for external forces.
But the moment it exits, those external forces, gravity and air resistance, immediately begin acting on it. So how is stability in flight achieved?
We rely on 2 distinct methods. The first, and most common for guns, is spin stabilization. Here, the internal grooves of the barrel imparts a rapid rotation to the shell.
Which creates a powerful gyroscopic effect.
A very powerful gyroscopic effect. This makes the shell resist any change to its axis, keeping it flying nose first, much like a rapidly spinning pop resists tipping over. This is used by all guns and howitzers.
And what about the method used by mortars and rockets, which typically don't have rifling?
That is fin stabilization. Instead of relying on rotation, fins are used to shift the center of pressure, or CP, backwards in relation to the center of gravity, the CG.
Think of an arrow or even a badminton shuttlecock.
That's a perfect analogy. The air pressure acts primarily behind the CG, which forces the nose to constantly align with the direction of flight.
Next, a truly vital concept for both performance and safety: obturation. Why is this sealing process so absolutely critical?
Obturation is the essential, perfect sealing off of the rearward escape of high-pressure propellant gases. If the seal fails, you get leakage.
Which is bad for 2 reasons.
At least 2. Leakage immediately drops the pressure inside the chamber, causing a severe, damaging inconsistency in your muzzle velocity. But more critically, those hot gases escaping rearward pose a catastrophic safety threat to the gun crew.
So the seal must be absolute.
It has to be absolute, whether it's achieved by the expanding metal cartridge case in QF systems or an internal obturator pad in BL systems.
Once that massive pressure has been contained and directed forward, the gun has to handle the resulting equal and opposite reaction.
And that is the principle of absorption of firing stresses or recoil. Newton's third law is uncompromising. The immense forward momentum given to the projectile generates an equally immense rearward momentum, the recoil.
And that energy has to go somewhere.
It does. It must first be absorbed by the specialized recoil mechanism, and any residual force must then be safely transmitted to the ground through the carriage or mounting structure.
And finally, the 2 structural requirements that keep the piece functional in the field.
First, mobility. The capability to be efficiently transported is obvious, but often underestimated is stability. The carriage or mounting must remain rigidly stationary during both the violent recoil, the backward movement, and the subsequent runout.
Which is the return of the barrel to its firing position.
Correct. Stability depends on a specific geometric relationship involving the gun's weight, its physical dimensions, and the height of the barrel's pivot point.
All right, let's dive deeper into the gun's anatomy. We've established that its whole purpose is to manage violence, but the sheer numbers are staggering. You mentioned pressure spiking up to 30 tons per square inch at the breech.
It's an incredible amount of force. And this is why the barrel isn't uniformly thick. It has to be significantly reinforced where the pressure is at its absolute maximum, right at the back end.
Right. The pressure gradient falls off toward the muzzle.
It falls drastically, but the breech must survive that peak. Now, to discuss the survival of the steel, we need to be very precise with our engineering vocabulary.
Okay, let's define the terms.
Stress is the external force acting on a body, measured as force per unit area. Strain is the change in shape or dimension that results from that stress. And the elastic limit is the critical boundary of strain.
The point of no return.
The point beyond which the material suffers permanent deformation is permanently damaged.
And within that elastic limit, we find a fundamental physical law.
Hooke's law. It simply states that within the elastic limit, the ratio of stress to strain is a constant. We call it the Young's modulus. If you exceed that limit, the material yields, which drastically compromises the barrel's ability to survive the next shot.
This precision leads directly to the safety requirements that govern how much pressure the armed forces will permit inside the weapon.
Absolutely. We define the elastic strength pressure, or ESP, as the absolute theoretical maximum pressure the barrel can withstand before catastrophic failure.
So the breaking point.
The breaking point. Then we define the permissible pressure, or PP, which is the maximum pressure that must never be exceeded in normal firing operations. The safety margin is built into the factor of safety.
Which is the ratio of ESP to PP.
Correct. And this factor is universally maintained at 1.5. This 50% margin ensures the barrel can handle significant variations in temperature or charge performance without risk of rupture.
So what exactly are those forces trying to tear the barrel apart? We identified 5 of them, all acting simultaneously.
Let's list the 5 powder stresses. The first 2 are the most critical internally. First is radial or compressive stress, which acts outward, trying to enlarge the bore diameter.
Okay, pushing outwards.
And the second is circumferential or hoop tension. Imagine the barrel as a set of extremely strong steel hoops or rubber bands trying to snap apart sideways. That's hoop tension. Both of these stresses are at their maximum at the inner layers.
Why are they concentrated on the inside?
Because the inner wall is the first line of defense. There's something called a stress concentration factor, which means that the interior layers have to carry a vastly disproportionate amount of the load to resist expansion.
So the outer layers aren't really pulling their weight?
They're uneconomically stressed, as we say. They're not carrying their full share of the load, which is why just making a barrel thicker and thicker is inefficient for high pressures.
What about forces acting along the length of the barrel? We're twisting it.
The third is longitudinal stress. This is a stretching ripple along the length, primarily caused by the driving band forcing its way through the rifling grooves. Fourth is girder stress, which is a static load, just the sagging or bending of the barrel due to its own weight.
Which is why barrels are thicker at the breech.
Exactly, to counter that sag. And finally, torsional stress is the intense twisting effect created when the projectile is forced to rotate so rapidly by the rifling twist. All 5 of these are fighting the barrel structure at the same time.
That brings us to the engineering marvel designed to counter these forces without adding excessive weight. Pre-stressing. The goal is to force those outer layers to share the load.
Pre-stressing is the application of calculated permanent stress to the barrel before it ever even sees a propellant charge. The modern primary method is auto-fretage, or self-hooping.
How does that work?
The process involves subjecting the interior of the barrel to immense hydraulic pressure. This pressure pushes the inner layers beyond their elastic limit, meaning they are permanently deformed or strained. However, the outer layers expand but stay within their elastic limit.
And when you release that hydraulic pressure, the magic happens.
That's right. The outer layers, which are still elastic, snap back inward, trying to return to their original dimensions. This contracting force puts the permanently strained inner layers under powerful, constant compression.
So the inside is being squeezed by the outside.
Constantly. So when the gun is subsequently fired, the enormous gas pressure must first overcome this pre-existing compression before it can even begin to apply tensile or stretching stress to the metal. It significantly increases the barrel's tolerance for peak pressure.
Wait, if permanently strained is another word for damaged, how can a damaged barrel be safer?
Because the damage, that permanent strain, is calculated and controlled. We intentionally strain the inner layers just enough to put them into a beneficial compressive state. This compression acts like a perpetual, invisible mechanical liner.
And the benefits are huge.
Massive. Reduced weight for maximum pressure, the ability to use lower grade or lighter steel, and the process itself acts as a self-test, ensuring the barrel is free from material faults before it's even pre-fired.
And for massive ordnance, that can't be hydraulically stressed like this.
For those, we use the built-up barrel method. This achieves the same goal, just mechanically. An inner tube is machined to precise tolerances. Then one or more concentric outer tubes are heated up, expanded, and fitted over the cold inner tube.
And as the outer tube cools.
It shrinks, mechanically placing the inner tube under compression and the outer tube under tension. It is old-school engineering, but it achieves modern results.
Moving to the rear of the gun. The breech mechanism. Its functions are to close the chamber, withstand that rearward thrust, carry the firing mechanism, and crucially, provide obturation. Let's confirm the key types based on how they achieve that seal.
The primary division is by the obturation method. QF, or quick-firing ordnance, uses ammunition with a metal cartridge case. Upon firing, the metal expands against the chamber walls, providing a perfect seal.
And the primer plug has its own seal, too.
Its own secondary obturating device, yes. Then you have BL, or breech-loading ordnance. This uses the charge in a cloth bag, so it requires an obturator pad and a specialized assembly within the breech mechanism itself to seal the gases.
What mechanism is common in modern QF ordnance to maximize the rate of fire?
That would be the sliding block mechanism, which operates either horizontally or vertically. Many are designed to be semi-automatic.
Meaning the firing shock does some of the work.
It does. It automatically unlocks the block, opens the breech, and extracts the spent case. This is essential for a high rate of fire, but due to the massive pressure, they absolutely require a robust mechanical lock, either a strut type or a pass dead center type, to prevent the block from being forced open during that critical 15 milliseconds of peak pressure.
And the high-strength, non-cartridge alternative.
The screw breech mechanism, typically found on BL ordnance, its strength comes from interrupted threads.
So parts of the thread are cut away.
Exactly. Instead of a continuous thread requiring multiple rotations to lock, segments are removed. This allows the crew to just push the screw into the breech and lock it with a partial, rapid turn. It combines immense strength with the operational speed required in battle.
Once contained, the charge needs ignition. How is that firing impulse delivered?
The armed forces use three main methods. Percussion, which is the mechanical strike of a firing pin on a primer cap. Electric, where a current from a battery or dynamo heats an embedded wire in the primer. And in BL ordnance, where there's no primer cap, ignition is often achieved by firing a separate small tube down a fire channel into the bagged charge.
We've contained the explosion. Now we must handle the recoil. The recoil mechanism is essentially a high-speed, military-grade shock absorber. It has two core components that form the elastic link.
The buffer and the recuperator. The buffer is the hydraulic brake. It consists of oil inside a cylinder being forced through precisely controlled apertures by the recoiling barrel.
Converting kinetic energy into heat.
Exactly. It converts the immense kinetic energy of the recoil into thermal energy, slowing and controlling the rearward movement safely. The recuperator is the energy storage system, typically using springs or compressed gas. Its job is to store that energy and then gently but firmly push the heavy barrel back to the forward or run-out position, ready for the next round.
And how do designers enhance stability externally? By managing the recoil force itself.
They use the muzzle brake. This is a steel framework of baffle plates fitted at the muzzle end. When the propellant gases exit the barrel at supersonic speed, they slam into these baffles and are deflected violently sideways and slightly rearward,
Creating a forward thrust.
a substantial forward thrust that works directly against the rearward recoil force. This significantly reduces the total trunnion pull, which we call F. By reducing F, the muzzle brake directly enhances the overall stability of the gun carriage, allowing the entire system to be lighter and more robust for the forces involved.
It helps maintain that critical stability formula, the dollar times LF times H3 relationship.
It does. It's a key part of it.
Finally, what is the specific operational requirement for cutoff gears?
They are critical for high-angle fire. When the gun is elevated highly, the breech might foul or strike the ground or the mounting if the recoil distance remains standard.
So it's a safety mechanism.
It is. The cutoff gear is an automatic device linked to the elevation mechanism. As you raise the gun, the gear rotates the buffer piston rod, which progressively reduces the area for oil flow inside the buffer. This creates greater resistance, automatically shortening the length of recoil precisely when needed.
Ensuring the gun doesn't damage itself.
Exactly.
The journey of the projectile is a split-second narrative in physics, divided into two distinct scientific domains. First, internal ballistics. That power sequence inside the bore which happens in a flash.
Usually 15 to 25 milliseconds, it's an incredibly fast, highly engineered chemical sequence. It begins with ignition. The primer flash ignites the propellant grains, immediately generating gases that reach $2,000
And the pressure builds violently.
violently until it hits shot start pressure. That's the precise pressure sufficient to engrave the Koppel driving band into the rifling and overcome the projectile's inertia, forcing it to start moving down the bore.
But because the propellant is still burning, the pressure doesn't just drop the moment the shell starts moving. It actually keeps rising.
Exactly. The pressure rises steeply, peaking at what we call Pmax, or maximum pressure. This peak pressure defines the design strength of the barrel. That factor of safety of 1.5 is referenced against Pmax.
Okay.
After this peak, the rate of pressure loss due to the increasing volume of the chamber finally overcomes the rate of pressure gain from the burning propellant, and the pressure begins to fall toward the muzzle.
And the most important moment, in terms of consistency and stability, is the all-burnt point, or ABP. Why must the armed forces locate the ABP closer to the breach?
Locating the ABP closer to the breach is crucial for three reasons that enhance performance and survivability. First, it ensures maximum consistency in muzzle velocity. Second, it maximizes the muzzle velocity itself because the gases get the longest possible time to act on the projectile.
And the third reason is tactical.
It is tactically vital. It allows the extremely hot gases more time to expand and cool before they hit the atmosphere. This significantly decreases muzzle flash, which otherwise immediately discloses the gun's position to the enemy.
So even after Pmax has been reached and pressure is falling dramatically, the shell continues to accelerate right up to the end of the barrel.
That's the core principle of the PV curve. Velocity continues to rise steadily right up to the muzzle, even as pressure, P, peaks and begins to fall. The expanding gas provides sustained pressure, forcing the projectile to accelerate throughout its entire travel in the bore.
Once the shell leaves the bore, we transition to external ballistics, where two main forces now govern its flight path.
First, gravity, the constant downward pull, attempting to draw the flight path into a perfect parabola. And second, air resistance, the retarding force that acts opposite to the shell's motion. Air resistance consumes enormous energy, making the actual trajectory significantly shorter and steeper than any theoretical parabola.
And air resistance, or drag, is multifaceted. It's not just one force.
Yeah.
What are the four specific components that designers have to fight against?
We have to engineer the shell to minimize all four. The primary fight is against head resistance, created by compression or shock waves forming at the nose. Second is base drag.
The suction behind the shell.
It's a low-pressure vacuum region created immediately behind the projectile. It significantly impedes forward motion and is minimized by streamlining the base. Third is minor skin friction. And fourth is excrescence drag, caused by unavoidable protuberances like the driving band.
And there is a specific velocity zone that causes maximum trouble for stability.
That's the transonic zone, spanning velocities just around the speed of sound. When a projectile has to pass through this region, air resistance changes rapidly and non-linearly.
It's unpredictable.
Highly unpredictable, and it severely compromises stability. Designers intentionally avoid building systems where the muzzle velocity hovers in this zone, preferring to keep systems definitively subsonic or highly supersonic.
Let's discuss the anatomy of the shell itself. It has to balance two competing efficiencies.
It's a constant balancing act between ballistic efficiency and tactical efficiency. Ballistic efficiency is all about flight performance, maximum range, and minimum dispersion. Tactical efficiency is about the result at the target carrying the optimal filling, whether that's high explosive, armor-piercing, illumination, or smoke.
And maximizing one often compromises the other.
Often, yes.
The biggest threat to the shell's stability in flight is something called the turning moment.
The turning moment is the continuous attempt by aerodynamic forces to flip the shell end over end. The angle between the shell's longitudinal axis and its actual trajectory is known as yaw.
Okay.
Because air resistance acts through the center of pressure, which is near the nose, while the center of gravity is further back, the airflow generates a moment that tries constantly to push the nose sideways and away from the trajectory.
And this must be resisted by that rapid rotation, the spin stabilization we discussed earlier. And the component responsible for generating this spin is the driving band.
The driving band is a critical, multifunctional component. Its four functions are essential. First, it imparts spin by being engraved into the rifling. Second, it performs the crucial task of obturation, sealing the gases. Third, it supports the projectile in the bore. And fourth, it acts as the ramming stop.
And the spin has to be perfectly calibrated. What happens if the shell is spun too fast or too slow?
You get catastrophic stability errors. If the shell is overstabilized, spun too fast, it precesses, it wobbles too slowly. The nose fails to dip quickly enough to follow the trajectory.
So it lands base first.
It lands base first, dramatically reducing its effect. Conversely, if it is understabilized, spun too slow, it precesses too rapidly, develops excessive yaw, and eventually tumbles. You can actually hear it. It's characterized by a loud whirring noise in flight.
Finally, even a perfectly stabilized shell is subject to sideways deviation drift.
Drift is the progressive lateral deviation from the original plane of departure. It's caused by 4 simultaneous factors that have to be calculated and corrected for. These include equilibrium yaw, the Magnus effect, Poisson's effect, and over very long ranges, the unavoidable rotation of the Earth.
We shift now from the physics of flight to the chemistry of energy release. We're dealing with an incredibly fast spectrum, from slow burning to instantaneous detonation.
The energy release spectrum defines our material choices. At the slow end is burning, just slow oxidation. Moving up, we hit explosion, rapid combustion. And at the extreme is detonation, an instantaneous disintegration of molecules creating a localized supersonic shock wave traveling at thousands of meters per second.
The difference between a controlled push and a catastrophic shatter.
An excellent way to put it.
Huh.
And a propellant is engineered for that controlled push. It induces a moderately high and sustained pressure to accelerate the projectile, not shatter it.
How do we classify these propellants?
By their chemical ingredients. Single-based contains only nitrocellulose. Double-based adds nitroglycerin, which increases the energy. Triple-based adds a third component like picrite. And composite propellants use an organic fuel and an oxidizing agent.
What are the ideal requirements for a propellant used by the armed forces?
It must meet strict requirements for regular ballistics, a uniform, regular burn rate. It must provide barrel protection, meaning it's non-erosive. It must offer cleanliness, minimizing residue, smoke, and especially muzzle flash. And finally, long-term stability and safety during transport and storage.
The key to controlling the propellant's output is how it burns. This relationship is codified in Piobert's law of burning.
Piobert's law provides the foundation for designing the propellant shape. It dictates 2 core realities. First, propellant burns simultaneously over its entire exposed surface in parallel layers. Second, and critically, the rate of burning, the ROB, is not constant. It increases significantly in direct proportion to the pressure inside the chamber.
So the geometry of the propellant grain is literally what controls the pressure curve inside the barrel.
Yes, by controlling the surface area available for combustion. Digressive burning occurs when the surface area decreases as it burns, like in a chord shape. The rate of burning slows down.
But the goal for high-performance systems is progressive burning.
Progressive burning is the goal. This is achieved with multitude or perforated shapes. As the propellant burns, the internal holes enlarge, constantly increasing the total exposed surface area. This increasing area helps to maintain high, sustained pressure as the shell moves down the barrel and the volume increases.
Now, let's look at the substances engineered for pure destruction. High explosives. They are designed for maximum brisance, the shattering effect. But to use them safely, we must follow the explosive train.
The explosive train is a vital safety and reliability sequence, moving from a highly sensitive component to the stable main charge. It starts with initiators.
The most sensitive components.
The most sensitive, easily triggered by a minor mechanical impulse. We classify them as disruptive, which produce a detonating wave, or igniferous, which produce a powerful flash.
But that small initiator isn't powerful enough to detonate the bulk of the shell filling.
No, that's the job of the intermediaries. They are the link components, designed to pick up that small impulse and rapidly build it up to a sufficient shock wave to ensure the main charge detonates fully and reliably.
And the final stage is the bursting charge.
The bursting charges, the main HE fillings. These demand maximum brisance, but also insensitivity to handling, stability, and sometimes smoke for recognition of the burst. You can think of it as a military version of a fuse box.
We turn finally to the brain of the shell, the fuse. The fuse functions the projectile, but it often needs an internal chemical amplifier.
That amplifier is the gain. The high explosives in the main shell are often intentionally stable and insensitive for safety. The gain is the small, highly sensitive charge that converts the fuse's relatively minor flash into the powerful detonating wave needed to trigger the main charge.
And fuses are classified by their tactical action.
Yes, several crucial types. Direct action, or DA fuses, require head-on impact and burst before penetration for max splinter effect. Gray's fuses are slightly slower, allowing slight penetration, ideal for dugouts. Time fuses operate at a preset time, and the sophisticated proximity, or VT fuse, is radio-operated, functioning at a critical distance from the target for an optimal airburst.
To ensure crew safety, the fuse must not function until it is fully clear of the gun tube. This process is called arming, and it relies on the intense mechanical forces of firing.
Arming is the mechanical process of moving internal safety devices into the functional, armed position using the forces generated by the gun. The three main forces are setback, or acceleration, which is the dominant force inside the bore.
Sudden rearward inertia.
Yes. Then centrifugal force from the rotation, which is dominant after leaving the bore. And retardation, where air resistance causes inertia pellets to creep forward, often used in Gray's fuses.
Moving from the mechanics of firing to the precision of hitting the target, we address the objective of the sighting system. It's pure applied geometry.
It is. The objective is to relate the axis of the bore, where the barrel is pointing to the line of sight, where the target is, so that the projectile's complex, curved trajectory intersects the target exactly. The manual process of setting the bore is called laying.
The ultimate goal of modern artillery is predicted fire, the ability to hit the target accurately with the first salvo. This relies on accounting for 8 specific factors that introduce error.
This is the accuracy chain. You have the accuracy of target fixation, inherent errors in survey, knowing where your own gun is, errors in calibration.
Individual gun wear.
Exactly. Errors in measurement of charge temperature, a major one. Plotting errors, day-to-day variation, sighting and laying errors, and finally, ammunition handling.
Let's focus on how modern technology minimizes these. Target acquisition used to be laborious.
It's vastly superior now. We use integrated observation equipment, laser rangefinders, UAVs, radars. A TIIOE can give you distance accuracy within plus or minus 5 meters.
And knowing where we are. The survey errors.
It's largely minimized by DGPS, Digital Global Positioning System. It gives highly accurate, real-time positional data.
And addressing the fact that every gun performs slightly differently due to wear, that's calibration error.
Modern systems are now self-correcting. We use muzzle velocity measuring equipment mounted right on the ordnance. It measures the MV of fired rounds and corrects the firing data in real time, compensating for the specific wear and tear of that barrel.
Here is where we introduce the crucial concept of charge temperature. Given all this modern tech, why is the simple temperature of the gunpowder still one of the major contributors to inaccuracy?
Because hotter gunpowder burns faster, that's Pylebert's law. Even a slight difference means a faster burn rate, which generates slightly higher pressure and thus a higher muzzle velocity. A minor change in MV translates into a major change in range, especially over long distances.
So if the ammunition has been stored inconsistently,
Some in sun, some in shade, the calculated correction will be wrong. All ammunition must be stocked under identical conditions to minimize this variable.
now, the single biggest source of persistent error, the one thing that is constantly changing, the atmosphere, MET management.
Atmospheric conditions, wind, air density, pressure, temperature, are highly variable and drastically affect the shell's flight path. We use computerized systems to build atmospheric profiles, but for maximum accuracy, the datum point procedure remains the most accurate method.
Explain the datum point procedure.
It involves firing several rounds at a known surveyed point on the ground. By observing the actual deviation, the battery determines the actual correction factor necessary for that specific gun on that day with that ammunition under those conditions.
So it counters multiple errors simultaneously.
It inherently caters for remaining survey errors, charge temperature variation, and all current atmospheric variability. It's the gold standard.
Once we have accurate data, the tactical goal is surprise and simultaneous destruction. We have several techniques for maximizing strike effectiveness.
The first is time on target, or TOT. This is an orchestration technique where different batteries firing from different locations adjust their fire times so that all rounds land on the target at the exact same second.
Maximizing shock and surprise.
Exactly. And then there's the truly cutting-edge capability for a single gun.
Multiple round simultaneous impact, or MRSI.
MRES. A single modern gun fires several rounds in rapid succession, using different charges and elevations. Each projectile takes a different trajectory, but they all arrive and impact the target simultaneously. It's an incredible capability.
And the ultimate solution that bypasses nearly all of these complex error calculations.
Terminally guided munitions, or TGMs. These are smart shells with onboard sensors and guidance. They adjust their flight path in real time. They eliminate the vast majority of ballistics errors and the need for traditional predicted fire corrections.
Our final section focuses on the mortar, the essential close support weapon that operates by different rules.
The mortar is defined as a high-trajectory weapon that typically passes its recoil energy directly to the ground through a heavy base plate. Its standard characteristics are: it is muzzle-loaded, has a smooth bore usually, and fires fin-stabilized subsonic bombs.
And that high trajectory is the main reason for its existence.
Absolutely. The high trajectory is what enables crest clearance and, crucially, the engagement of targets in dead ground or on reverse slopes, positions that are inaccessible to the flat trajectory of a gun.
What are the main operational trade-offs?
The advantages are its simplicity, high mobility vital for avoiding mortar locating radar, and flexibility. The disadvantages include a limited range, a significantly long time of flight, and the need for bedding in, which means poor initial accuracy.
Let's discuss the unique mechanical challenge of muzzle-loading mortars: windage.
Since the bomb has to be dropped down the front of the barrel quickly, there must be a necessary gap between the bomb and the bore walls. We call this windage.
But it's a source of inefficiency.
It is, as propellant gases inevitably escape around the bomb, reducing the pressure and lowering the overall muzzle velocity.
There are exceptions, though, like rifled mortars.
Yes, used to improve accuracy at longer ranges by imparting spin, but rifling complicates the loading process because the bomb's driving band needs to be aligned with the grooves, which inevitably slows the rate of fire.
And how is the mortar's lethality generated?
Primarily through fragmentation, not blast, due to the low terminal velocity. The goal is to shatter the bomb body into optimal 1-gram fragments, often using spheroidal graphite cast iron to get a high yield.
Range control is managed by varying the secondary charge systems.
Correct. Small donut-shaped propellant increments are added or removed from the tail of the bomb. It's a simple, stepped control over muzzle velocity and range.
Lastly, circling back to the trajectory, the high arc creates a critical tactical vulnerability known as apogee vulnerability.
At the peak of its trajectory, the apogee, the bomb has minimal velocity. Because of this near-stationary state relative to the air mass, its flight path is highly susceptible to even subtle changes in meteorological conditions. This makes achieving precise, predicted fire very difficult.
Okay. To synthesize this extensive revision for our learners, let's do a quick top-down summary.
We began by defining artillery through its components ordnance and the stabilizing carriage mounting, and categorized equipment by trajectory. We established the necessity of the design compromise and solidified the definitions of accuracy versus consistency. The operational principles emphasize spin stabilization versus fin stabilization and the absolute requirement for obturation.
We analyzed the barrel survival mechanics, defining stress versus strain, and the critical factor of safety of 1.5, emphasizing how auto-fretage is used to manage forces like hoop tension. We detailed the recoil system, the hydraulic buffer, and the recuperator, and how the muzzle brake enhances stability.
We moved into ballistics, marking the importance of the all-burnt point for consistency. In flight, we noted how air resistance and gravity shape the trajectory and how the driving band resists the turning moment. In chemistry, we differentiated the controlled pressure of propellants from the supersonic shockwave of high explosives, managed by the explosive train and armed by setback and centrifugal force.
Finally, we covered modern targeting, confirming that achieving predicted fire requires managing 8 error factors, with charge temperature and meteorology being major contributors, often corrected most effectively via the datum point procedure. Tactical strike effectiveness is now dominated by TOT and MRSI.
A truly comprehensive overview.
It is. Now, for the final provocative thought for you to mull over, learners. Since propellants burn faster under increasing pressure, and the force of recoil dictates gun stability, how might a future, more powerful propellant one that generates higher pressure, faster force, a complete redesign of the gun's recoil system and muzzle weak, just to maintain that critical factor of safety of 1.5?
It's a fascinating engineering problem.
It is. That's all the time we have for this deep dive. Go review those definitions, and we'll catch you next time.